Hi, everybody. Welcome to the last the last lecture. Excuse me. There's not really much left to say. There's just chapter 5, and chapter 5 is like 20 slides long because we don't do MO theory. Um, so let's do some quick announcements. I sent out a bunch of announcements last night. One was about the exam. The exam went pretty good, although I had some issues on my end. Nothing that was your fault. Purely technical issues that I don't really know who to blame. I blame Canvas usually. That gets away from me, or whatever. So I sent that one out. What else did I send out? I sent out a message about grades. I know a bunch of people were asking about, hey, what should I do if I want to get a V? And the answer is you email me. I do need your permission to do that, so I will ask you to confirm. Odds are, if you are requesting a V, you're probably not here watching the last lecture, and you're just reading the announcement, though. Yeah, late night for me. I usually work that late anyway. And when I say work, I mean that's just when I'm up. So I might be working on school stuff, or I might just be playing Persona 5, which is what I've been doing lately. And then finally, words of encouragement. Don't give up. We are almost done. Please don't collapse before the finish line, because I will drag you kicking and screaming over it so that you can finish this class. Why? Oh my goodness. Hold on, sorry. So another chemistry instructor is messaging me on Steam. I want to buy you a present. I'm giving a lecture right now. And let's see what he says back to me. Oh. Yeah. Oh. Yeah, Persona 5 is really good. Gosh, I don't even know where I am. Oh, yeah, that's right. Okay, so on the screen you can see that the quiz, the lab, and the final are all due on the same day. Now, I have given you a week to do that, so make sure that you are using that week. I went and looked to see how many people had done the quiz, and it's about half or so. So that's good. But make sure you are also spending the time before the exam, preparing your lab as well. Don't rush it all to the last second, because you're going to have a really bad Thursday night. You're going to be up as late as I was. And the final is everything. Yes, that's correct. Chapters 1 through 6. It was not Steve. I know many chemistry faculty members. We're all nerds, it turns out. Yeah, don't do that. It turns out that that's not a good strategy for success. Furthermore, doing those preparatory activities, so like the quiz and stuff, that's a good way to study. Because remember, just doing anything related to the content counts as studying. If you take the Chapter 4 quiz, that's a good rubric to see how well you know the Chapter 4 stuff. And if you get 99%, you don't need to study the Chapter 4 stuff. Go study Chapter 5 or 2 or 6 or something that's been a while since you've done. So use all those resources to your advantage. Make sure you ask me questions. Not many people are asking me questions about the content of the course, so I'm guessing that you have it all under control. But if you have questions, I'm going to be around. So today and tomorrow, last days, do that. I can't answer content questions on the day of the final, unfortunately. So if you ask me, like, how do I calculate molarity on the day of the final, I'll say, I probably won't say anything. I just won't reply to that email because I don't know a nice way to say, sorry, I can't do that. Anyway. I really don't understand why the textbook is... Yeah, Google it. I mean, I can't stop you, right? I don't really understand why the textbook is organized like this, where Chapter 3 is just like, hey, let's spend 4 weeks on it, and then Chapter 5 is, oh, well, we could do this in a day. We're not going to actually do molecular orbital theory because it is... I like MO theory. I think it's super useful, but other faculty don't really use it. You might use it in 261, and then they'll teach it to you there, I guess. But the other two are pretty important. We want to talk about how bonds are formed with orbitals. So in Chapter 3, we talked about shapes of orbitals. We're going to use that again today. You're going to see my wonderful drawing skills in action here. And then we're going to talk about hybridization, which is really just a code that you're going to assign to a geometry. So if you know all the Vesper geometries, you're going to now assign a letter code to them with hybridization. And we're going to talk about what that means. And it probably won't take that long. This slide has sound effects on it, so I need to turn this up. All right, hopefully this won't be too loud. On the screen here, I have a bunch of orbitals, and so these are lined up as pairs. And what we're going to do is I'm going to take something in the left column, and I'm going to move it over to the right column, and I'm going to try and overlap them without putting the nuclei, which are at the center of these coordinate axes, on top of each other. So, like this guy right here, you can't see my cursor because I wasn't clicked on the screen there. This guy right here is going to move about to here, but not right on top. Now, in these diagrams are... Oops, there we go, okay. Are our electrons. So, like, in this 1s orbital for hydrogen, for example, there might be an electron in each of those orbitals like that. If I were to move these two orbitals into each other, there would be a region that overlaps. And what the electrons would do is they would go into that overlapping region. So covalent bonds occur when you have electrons that are shared between atoms, like we said before. But the key is that those shared electrons stay in the overlap region. Now, not all of these combinations are going to overlap. So if I put these two s orbitals together, this is obviously going to work, because these two spheres are just going to go whoop, and part of them is going to pass through. There you go. That was a lot louder than I expected it to be. Let me turn my volume down. Had to get my game show buzzer out for that. So this one works, and the reason for that is because two spheres have a geometry that allow them to overlap. So you can't really tell, but the sphere on the right is passing through the sphere on the left. It's not superimposed behind it. That's how the graphic will work in PowerPoint. Now, if I do the same thing for this sphere right here with this p orbital, the p orbital is pointed in the wrong way. So my sphere is actually going to kind of go in between here, and you get a result that looks like this. So this sphere and this p orbital did not overlap. So I cannot combine an s orbital and a p orbital along the x-axis. For the same reason, I can't do that with this z-oriented p orbital. They just don't overlap. You can see that there's a big space here. But this p orbital right here is oriented along the y-axis, and that's the direction that my orbital is traveling along. So if I move this guy over, that'll overlap just fine. So when we make covalent bonds, what we need to do is orient orbitals. Sorry. Yes, I apologize to any pets out there. They're like, why is a doorbell going off? What we need to do to make covalent bonds is to overlap orbitals in orientations that allow that to happen. So these two combinations, the s orbitals overlapping and then an s orbital overlapping with a p orbital aligned in the correct direction, should work. Now, if I replaced one of those s orbitals with another p orbital, I could do that over here as well. This would also work. And when I get my electrons, they would pair in these overlapping regions right here. Now, what do the different colors mean? The different colors are the phases that we talked about very briefly in Chapter 3. You might remember that I said something about phases, that they exist. We're going to talk about phases a little bit more today. So that's our goal. We're going to overlap orbitals and then put one electron from each orbital into the overlapped region. All right. Now, there is another way to do this with p orbitals, and that is if you have them side by side here. Oops, I didn't mean to mark that. If you have them side by side like this, they actually overlap in their lobes. So right here and right here are overlap. But you'll notice that in the middle here, there's no overlap. Now, this is actually really interesting, and I'm probably going to get ahead of myself here. But while it's on the screen, we're going to just do this anyway. So I'm going to draw a line through the nuclei. Kind of missed on the last one. That's okay. And what I should do is I should also put my electrons in the overlapping region. Now, when we form covalent bonds, the electrons might be between the nucleus, or the nuclei, I should say, or they might not. So, for example, this pair of electrons is between the nuclei because I drew that line between them and it's on that line. This one is too, and this one is too. But this one up here isn't. We're going to assign a term to differentiate these two types of bonds because the ones that form between nuclei are going to be very different than this one over here. So we're going to call these... We're going to call these sigma bonds. And so that little, like, O with a hat, or a bandana, or I don't know, or like the ninja bandana sort of thing. That is a sigma. That is the Greek letter lowercase s. And the way to determine if a bond is a sigma bond is that the electron pair in the bond is along the internuclear axis. And so this is the internuclear axis, that blue line that I drew. If your electrons fall between the nuclei, they are on the internuclear axis. And therefore, the bond that you are making when you overlap your orbitals like that is a sigma bond. Now, the other type of bond that you can make, like this, is the pi bond. And you know you have a pi bond when the electron pair in the bond is not on the internuclear axis. Okay? And in fact, there is no electron density on that internuclear axis because that's a node for the p orbital. Now, something I do want to point out while these p orbitals are on the screen here. This electron pair that I am circling here is also simultaneously in this position down here too. Remember that the p orbital is both sides, and the electrons are wave functions. They act like waves, so they're just sort of everywhere at once. So when you draw electron pairs, draw, like I can have you draw on canvas, right? When you are drawing these for electron pairs for practice, we'll say, you only want to put one pair in the overlap, because this overlap on both sides is just one bonding orbital. So just be careful on that. With the sigma bonds, it's very easy, because there's only one region that overlaps. But for pi bonds, there will always be two regions, and both of those regions together are the bond. And you can only ever have two electrons in an overlap. Oh, and there we go, sigma and pi. I was just ahead of myself there. So, to review, we want to label sigma bonds as any bond that goes along the internuclear axis. And a pi bond does not go through that. And I wrote here it goes parallel, but not through it. So you're going to be asked to identify bonding combinations of orbitals. Like, I might just put these pictures on there and say, what type of bond is this? And you would check sigma or pi. Because it has to be one of those. There aren't any other options, right? And then what we're going to do is we're going to correlate sigma and pi bonds to Lewis structures that we've been drawing all along. Because it turns out that sigma bonds are going to be the first bond you draw between two atoms. And a pi bond is going to be any other bonds beyond that. So if you drew a double bond, you have a sigma and a pi bond. If you drew a triple bond, you have a sigma and two pi bonds. We're going to draw pictures to show how that works. But first I have to sneeze. One of these days I'm not going to hit mute in time before I sneeze. I sneeze really loud, so I apologize. Whenever we draw a Lewis structure, the first bond between any two atoms is a sigma bond. And any bonds after that are pi bonds. And I forget if I put a picture down here. Oh, that's just a summary. Okay. So what I'm going to do is I'm going to draw a molecule here, just really quickly. So, And we'll do this. There we go. So on a test, I might ask you, identify all the sigma bonds and all the pi bonds. And what you do, so I would say, okay, sigma we'll do in red. So The first bond in any bond between two atoms, I don't know what happened to here, but that's okay, is going to be a sigma bond. So there'd be 1, 2, 3, 4, 5, 6, 7, 8. I circled 8 sigma bonds there. And then pi bonds would be the second or third bonds that I make. And so this structure would have 3 pi bonds in it. Now that's the theory behind sigma and pi bonds. We're just going to arrange them in space so that the electron density fits. But what does that look like from an orbital perspective? That's where hybridization is going to come in. Because we're going to quickly hit an issue here when we talk about geometry and how valence bonds work. There's our summary there. So if you have a single bonds are always a sigma bond. Double bonds are always a sigma bond and a pi bond. And triple bonds are always sigma bond plus 2 pi bonds. All right. On the screen is a molecule for you to try counting. So in the chat, type in the number of sigma bonds there are and the number of pi bonds. Because, hey, test question. You're going to see this on the final. Here's a molecule. Count the bonds. While you do that, I got to go fill my water and blow my nose, apparently, because it's, I guess, allergies or something. So I'll be right back. We'll go over the answer. Alright, I'm back. I had to open a window and pet a cat as well. Alright, so let's count all the bonds. So the first bond between any two atoms is always sigma. So 1, 2, 3, 4, 5, 6, 7. And then any double or triple bonds are pi. And there you go. Very good. Easy as pi, right? Do-do. Now I want pi. I have pi, actually. I might go get that during the break. Alright. Now, I showed you this picture in Chapter 3 when we were talking about orbitals. And back then it probably made no sense, but now it might make a little bit more sense. When I have two orbitals that I bring together to overlap, there is an attraction between all three entities in the system. And what I mean by three entities is the following. So if this is my s orbital, and this is my s orbital. You know, let's do this in not bright green. A color that's easier to see here. So I'm going to have a little tiny bit of overlap. I'm going to draw this picture right here in the middle. In the nucleus are protons, and protons are positively charged. Now, by themselves, these two would just push each other away. But in the overlap region are my electrons. And so I have this attractive interaction between the protons and the electrons in the middle, and then the protons on the other side. So I make this little unit. Now, because of Coulomb's law, the closer you get things, the stronger the attraction, right? So if I can get the protons even closer to these electrons by just overlapping even more, now you can see that the protons are actually much closer to the electrons that were in the middle there. And so I make a stronger interaction. But if I get too close, then the protons start to see each other. And so right here, in this diagram right here, the two blue dots that I wrote are the nuclei, and they're just too close, and they repel each other. What that means is that there is some optimum distance that any two orbitals will settle to next to each other. And that's going to depend on both the number of protons in the center of the atom, so the effective nuclear charge, essentially, and the size of those orbitals. That's going to dictate the bond length. Now, you can't really calculate bond length. There's no formula to do it. You have to do it experimentally. And we're not going to talk very much about bond length in this class, other than what we've talked about in Chapter 4, which was bond strength and bond length are correlated. Stronger bonds are shorter for the reasons you see here. All right, I'm going to erase all this so I can put the text up. But the takeaway is that if you have some overlap, at some point you will get to the best optimum bond that you can form before the nuclei start to push each other apart. And that'll correspond with whatever bond length and strength you have. Now, we could combine any orbitals that we want to make all sorts of different shapes. Let's try and do that using some common molecules that you've probably seen before. So this premise is called valence bond theory. Valence bond theory says I'm going to use valence electrons, and I'm going to take their orbitals, and I'm going to combine them. And when my orbitals overlap with each other, I put the electrons in that region, and I create a molecule. And this theory is great on paper, and we're going to see that it falls apart very quickly. First thing we want to talk about is that when we form a bond, we have to use unpaired electrons, just like before. Remember when we started drawing covalent bonds with Lewis structures, and I said, hey, connect the dots. Just pair the unpaired ones together and just draw a line between them. We're going to do the same thing. We're going to overlap orbitals and take the unpaired electrons on each atom, put them in that overlap, and then we'll have a pair. Any orbital that has a non-bonding pair, or we should just say any orbital that has a pair of electrons already, becomes a non-bonding pair because it doesn't need any more electrons. It's content, and so it just sits there. So let's show that example with water. Oh, I have H2S. Same thing, that's fine. So here's what we're going to do. I'm going to draw a picture of this. So we've got hydrogen, which has 1 electron in it. I've got another hydrogen that has 1 electron in it. And then for sulfur, here's what we're going to do. So I have a 3s and a 3p orbital. So I got to draw 3s first. And it's got electrons already in it. And you can see that I put those on the side for a specific reason, because now I'm going to do this. Here's my 3p orbital, and it has electrons in it. And then I have another 3p orbital, which would go this way. But it only has 1 electron in it, so we'll do that. And then I'll draw the other orientation, which would be like this. We're going behind it now. And it has 1 electron too. And so what we're going to do is we're going to take this electron right here on the hydrogen. We're going to pair them here. I'm going to pair these here. And then what will happen once I move everything in there, I unfortunately chose the same color for hydrogen as that one, but that's okay. Is that I will create this molecule. And so my H2S would look something like this, where there was kind of a bond angle that was like this. And you can see my electrons are just sort of floating around in the other orbitals. And if you're looking at this and thinking, well, that seems kind of close, but there's something kind of wrong here, then you're exactly on the right track, because there is something totally wrong here. Not just that it looks hideous, but that, there's something about the geometry that doesn't make sense. And so that's why valence bond theory kind of falls apart. In principle, it makes sense. We're going to overlap orbitals from each atom and then create a overlap region where the electrons go and sit there to form the bond. So these are the electrons that we paired. There's our molecule. I got to erase my structure, unfortunately, to see that. And do I have... Let's see here. Yeah, there we go. So there we go. When I tidy up the Lewis structure, you can see where the electrons ended up. So the ones that have the blue arrows connecting them formed the bonds, and the ones that are circled are the non-bonding pairs. Now, I showed you where those exist as orbitals, and that was just a hot mess of a drawing. And in reality, the reason that it's such a hot mess is because of the problems that we're about to discuss. since you all just did Chapter 4, you should know what the bond angle is between these two entities. What's the bond angle between this right here? Yeah, it's 109.5. Very good. Now, we're going to keep that number in mind here. I'm going to quickly draw my molecule again. Yeah, I am going to use only one color this time for sulfur. So there's all my orbitals. So I got 3p and 3s right here. And when we put our hydrogen on here, we had one of them down here and then one of them over here, we'll say. But what would this angle be in this structure? Yeah, that one looks like 90, right? So which one's right? And it turns out the answer is, well, this is the angle that we observed, so is this model any good to us? And so that's a major issue. How the heck do we get... I forgot that happened. Darn it, I like that sound effect too, so hold on. So, how do we get to this situation where we have something that's so eloquent, it makes sense. Here's our non-bonding electrons. Here's our bonding electrons. And then, yep, totally wrong. There we go. Like, how? Like, how can something work out this great and then just be bogus? And the answer is that, in reality, what the orbitals are doing when they form these interactions is they are not just combining with the things that they're bonding to, but they're also sort of combining with themselves to form averages that then participate in bonding. And what that means is that instead of having a distinct 3s and 3p orbital, what we're going to do is we're going to do this. I'm going to add them together and then divide by the average. And so this is what's known as hybridization. So in the next section, what we're going to talk about is how the heck do you get all of these p orbitals that I've stacked on top of each other to make a tetrahedron? And the answer is you don't. You have to combine them to do what we observe in very specific molecules, like CH4. So if this was our tetrahedron, here's where our H's would go at the corners of this tetrahedron. But if I had this here, I'd have to have an H on like 3 of the corners, and then the fourth one would end up being in the s orbital. And so it's like, where does it go? So we need to match our model with what we see. We see tetrahedrons all over the place when we have 4 electron pair groups around a central atom. And so that's where hybridization comes in. And that's what we're going to talk about for the next half of the class. Yeah, we're almost done, believe it or not. All right. Let's look at this from an electron configuration perspective. If this was carbon, there would be a 1s orbital down here, but we don't care about non-valence electrons. I'm going to just do this. Valence theory says that carbon should make only 2 bonds because there are only 2 unpaired electrons. And what I should observe is something that looks like this for carbon when I draw it connected to a structure. You've done a lot of Lewis structures at this point by now. How many times have you put an electron pair on carbon? Write your answer in the chat. How many times have you drawn this structure that I drew here? It's not a trick question. Yeah, never, right? This is not something that you have ever drawn, because this completely breaks the rules. For one, there's no octet. 2, its formal charge is like, what? Very confusing. We just have never seen this like this, right? So, in reality, this can't be how carbon behaves. In fact, a better way to describe this would be if I could somehow do this. I didn't put 2p over there. Right, if I could unpair them all, then now I could make 4 bonds. So 1 bond, 2 bonds, 3 bonds, 4 bonds. That would be much better, right? But there's this energy gap to deal with. It would cost us energy to do this, so this wouldn't naturally happen. But what if I took all of these orbitals and I took their average? So I took 2s plus all the 2p's and I divided by 4. If you take the average, you get some result. And that number will be between the 2 extremes. So if 2s is in lower energy and 2p is in higher energy, the average will be closer to 2p because there's more of them. So I'm going to draw a dotted line like this. But if I take the average energy of these things, then what I can do is I can say, well, now they're all degenerate, and I can do this. And now it makes sense to have them arranged like that. This process of averaging the energies of our orbitals is called hybridization. What we do is we take s orbitals and p orbitals and we mix them together. We combine them. And when you do this, you create new orbitals. The orbitals that come out are representative of what went in. So for instance, I had 1 s orbital and 3 p orbitals. Notice I'm using the word numbers here, not to confuse. Since I had 1 s and 3 p orbitals, I will call these orbitals sp3. In other words, what you put into the atomic blender when we hybridize is what you get out. If instead I only hybridize 2 of my p orbitals with the s, I would get sp2. And if I hybridize just 1 s and 1 p orbital, I would get sp. We're going to talk about why you would do that later on. Alright. I'm going to put a bunch of text on the screen that'll basically say exactly what we just did, but that's okay. So here's our original carbon once again. I need to have all my electrons unpaired. So if I were to combine my orbitals by hybridizing them, in other words, I take the average, and I put all of the energy levels at where that average goes, I then have 4 degenerate orbitals that I can then separate out my electrons along. Thanks, Hundred World. You're the greatest. Now I can hybridize whatever combination of orbitals I want. If I hybridize only certain orbitals, the ones that do not get hybridized are left over. And they remain whatever they are. So they would say p orbitals, for example. Because I hybridized 1 s orbital and 3 p orbitals, for a total of 4 orbitals, that's why I got 4 out. It would be like saying you put 4 cups of liquid into the blender to make like a drink or something. Like you're making fruit punch, so you put 1 cup of apple juice and 1 cup of orange juice and I don't know, whatever. The total volume at the end would be however many cups of stuff you put in. I don't know what the recipe is for fruit punch, so that might be disgusting. Ew, who puts apples and oranges together? Gross. It's like he's never had fruit. I actually don't eat sweet stuff that often, so. But since we put in 4 orbitals on this page right here, here's our 4 orbitals right here. 1, 2, 3, 4. I get 4 of them out. 3, 4. The name, like we said, is going to be based on what you combine. If you combined an s and then 2 distinct p orbitals, you would make sp2 orbitals, and there would only be 3 of them. So we're going to do that later on. We're going to do sp. We're also going to do sp3d and sp3d2, and you'll see where all these crazy geometries come from. When you are looking at bonding in a molecule, hybridized orbitals come into play. If you are looking at atoms by themselves, the atoms do not be hybridized. And the reason for that is they don't need to. Anything that is not participating in bonding is not hybridized. Anything that has bonds connected to it is hybridized. All right. This is a picture of what s orbitals and p orbitals look like when you combine them together. Since we are taking the average, the result is going to be that my orbitals look mostly like my p orbitals, but have a little bit of s character to it. And so these right here, these bowling balls that are oriented in these random directions, not bowling balls, but bowling pins, are oriented in random directions relative to the center of the tetrahedron. Because there are 4 of them, we can overlap them in such a way that we fill the corners of the tetrahedron and we get 109.5 degrees as our angle. When I draw these orbitals later today, what I'm going to do is I'm going to say, okay, here's my carbon. And then when I draw orbitals over it, I'm going to ignore the tiny lobe. So we're just going to ignore these guys. It exists, but we only care about the part that we're going to use to overlap. So this is what my tetrahedral sp3 carbon will look like. And then I think CH4 is actually on the next slide. There you go. So you can see where my diagram came from. And so if I were to take this molecule and pull the bonds apart real quick, here's my sp3 orbitals. And carbon has 4 unpaired electrons, so I'm going to put them in each of these spots. Yeah, suddenly Chemistry 161 became this class that's focused on, like, balloon diagrams. And so you can see, as I'm drawing this, how we got the structure on the right. And there you go. So all of my H atoms had one electron with them. They brought that to the carbon party. They all pair up together, and this is how you get CH4. Now, if this were in person, I would make you draw these. And they're great fun to grade, I can assure you that. So what I'm going to have you do instead is I'm going to have you open up your Paint program on your computer and save your picture as a JPEG and send it to me. So you use the mouse to draw. No, I'm just kidding. Absolutely not, right? I have a stylus, and this is the best that I can do. I can actually do this a lot better on the board, but c'est la vie, right? Alright, so that's how we make sigma bonds. By overlapping hybridized orbitals. Party Clown 101. There you go, yeah. Now, it turns out that anything that has a tetrahedral geometry is always going to need sp3 orbitals. Yeah, everybody should have a Paint program. I think it's default. Well, if you're using Linux or a Mac OS, it's probably called something different. I did open this, okay. So let's... Oh, that's too big, actually. Is this going to capture that? Okay, cool. It turns out that if you have a specific geometry... This is way too big. The hybridization that comes out of that will always be linked to it. And when I say geometry, what I actually mean is that the electron pair geometry. So let me write down all the possible geometries here. And so this is the one that we just had for carbon in CH4. We made it sp3, and its shape was tetrahedral. It turns out whenever you have a tetrahedral carbon, or tetrahedral anything, the hybridization is always sp3. Likewise, if we have trigonal planar, the hybridization will always be sp2. And the reason for this, we're going to show very shortly. I'm just going to show you all the hybridization combos while I was thinking about it. Linear is sp. And then 5 and 6, you might be thinking, well, wait a second. There aren't any more orbitals to combine to get 5 and 6. Well, it turns out, if you're in n equals 3... then 3D orbitals become available. So if I needed 5 electron domains, I could go bang, 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 and go sp3, d. And then if I needed another one, I could do that. And if I needed another one, then it's still available, and I could just keep doing this all damn day if I wanted to. But what the heck geometry has 7? Well, we don't really go into this geometry in this class. However, you could find a molecule that has 7 electron domains around it. In fact, if you look up this molecule, I believe that XaO2F2 has 7 electron domains around it. And so you just draw whatever the geometry is for 7 electron domains, with those balloons, put one unpaired electron around xenon in each of those balloons, or any pairs if you have non-bonding pairs, and then just connect all the stuff. So this is going to be a task that you're going to have to do as well. I'm going to show you a picture of a molecule, and I'm going to say, like, click on the sp2 carbon, or click on the atom that is sp3d, or what hybridization is this picture? That sort of thing. So we're going to link up geometry with these letter codes here. And so whatever the electron pair geometry is, it's always going to correspond to one of these letter codes. Okay? And that's really it for hybridization. Can you remember the letter code? Sure you can. All right, so the rest of this lecture, we're going to show you just the theory behind this. And of course, there's no way I can make you draw any of this, because it's Canvas. Like, what am I going to do? I'm not going to make you buy PowerPoint or buy Photoshop and start doing this. But there will be some interesting topics that we're going to discuss as we go through this. Okay. We are due for a break, though. So what I'm going to do is I'm going to take our break now before we get into this nitty-gritty detail. We'll put this on the screen. Oh, I got to open the timer for the last time, don't I? All right, so I'll start the clock. We'll see if I land exactly on 10. Probably not. I'll start the music again. We'll see in a bit. Oh, that was really close, though. You see, I couldn't land on 10 minutes because then I would have to play the Price is Right sound, and that would wake up Leia's dog. We don't want that. I'm just being thoughtful. All right. So, back to our discussion here. So I listed here... Oops, that's the wrong window. I listed here the different geometries that you'll encounter with molecules and the different hybridizations. Yeah, it does keep going. Past 6. It goes all the way up to 9, actually. But we'll never actually use 9. In fact, we'll never actually use 7. So the ones 2 through 6 here, the ones 2 through 6 here are the relevant geometries and the hybridization that links with them. For the last hour, what I want to show you is how we get sp2 and what that means. Like, what do we do with that extra p orbital? Well, there's a very important thing that we're going to do. First, I want to show you ammonia, which is also tetrahedral. In fact, if you drew its Lewis structure, I'll just draw it quickly down here. You'd say, oh, it's tetrahedral. It's got 4 electron groups. Here's the electron pair up here, and there's these guys. And those little circles that I'm drawing actually look very close to the orbitals where the electrons would go. And so you can see that in my diagram I had 5 electrons. 2 of them had to be paired. That's going to be my non-bonding pair. And then each of these gets bonded to an H. And so NH3 has 3 sigma bonds and an alone electron pair, which goes in the 4th sp3 orbital. How do you make double bonds, though? This is where the p orbitals come in. Remember that in order to make a double bond, I had to have a pi bond. And in order to get a pi bond, I had to do this with adjacent p orbitals. What this means is that in order to form a double bond, I have to reserve a p orbital. And the p orbital has to be unhybridized. If we hybridize away all our p orbitals, then we don't have anything that we can overlap side to side. So what we had to do is we had to do, instead of doing this, we had to do something like this. And then the extra p that we didn't use hangs out by itself. So this is where sp2 and sp come in. If I make sp2, I will have 1 unhybridized p orbital, and I can make 1 pi bond. But if I do this, I could have 2 unhybridized p orbitals and an sp orbital. And so I could make 2 pi bonds. And when I say 2 pi bonds, what I generally mean is that I could either have like a double bond coming out, or I could have a triple bond. Both of those would be 2 pi bonds. Oops, I drew over my thing. There we go. So there's that picture again. We use unhybridized p orbitals to make pi bonds. So we need to save p orbitals when we're hybridizing. In other words, if I take my diagram here for carbon, and I say, well, I know this molecule has a p or a double bond. C2H4, if I drew its Lewis structure, would look like this. Wow, well, that's not what it looks like. That's just terrible. So we should all be able to draw this Lewis structure. And you'll notice, oh, it has a pi bond in it. It has a double bond. I need to save a p orbital, so I'm going to reserve it. That yellow highlighted orbital up there is going to just get carried over. And we're not going to touch it. But the other 3 are going to get blended. And then the orbitals that we form will be of equivalent energy, because we've averaged them. Since I put in an s orbital and I have 2 distinct p orbitals mixed in, I will get sp2 as a result, and I have a leftover p orbital. Now, what is that going to look like? Well, we know it's going to be trigonal planar because that's the geometry that we have here. But what I'm going to do now is I'm going to go new. I don't know. Oh, it is going to... Okay, so I got to do it this way. Control-Shift-N? Yeah, there we go. New layer. My on said layer. Yes, okay. So what we're going to do is we're going to draw this sp2 orbital. Not in white. That's not going to help anybody. So these are the orbitals that are left over. So I'm going to first draw the p orbital. And I'm going to draw it going up and down. Like so. Let me put a big dot in the middle. That's going to be the nucleus of my carbon. And now, so my p orbital is in black. I'm going to do the sp2 orbital in blue here. And I'm going to draw my sp2 orbital in such a way that it doesn't overlap with the p orbital that I drew. In other words, this is my planar part of my trigonal planar. And then what I'm going to do, this is going to get wild, you guys. We're going to put another orbital, or another carbon right here. I'm going to put this p orbital like this. And I'm going to put its trigonal planar orbitals like this. And so this is going to be my sigma bond. This is where my electrons would go to overlap. But my pi bond would be if these guys overlap. Now, I didn't draw them close enough. So what I'm going to do is I'm going to kind of just cheat. I'm going to just do this. There we go. Now it's like they're overlapping, right? So in this shaded region that I'm going to lightly shade in with a pen because I have a pressure sensor on it, so I don't have to draw thick lines. There we go. That's the overlap of my p orbitals to form the pi bond. So this is right here. So everything in the shaded region is my pi bond. Everything in the blue region in the middle is my sigma bond. And then these other bonds would be sigma bonds that go out to my H's. So if I were to draw this molecule here, here's my sigma bond between all of my stuff. And then my pi bond would be this second one. There you go. That actually looks a lot better than I was expecting it to. So this is how the orbitals look in C2H4 with a pi bond. Okay? Pi bonds will always go around the internuclear axis. And the orientation that they have to take is dictated by what the other orbitals already occupy. For example, if this was a coordinate plane, and I labeled it this way, where X was in this direction, like front to back, Y was left to right, then Z would have to be up and down. Since X, Y were already used up by my sp2 orbitals, then the z-axis is where the p orbital has to go. It always has to be perpendicular to the plane of the trigonal planar geometry. Now, if I do SP, I'm going to have a linear orientation, which means that I'm only going to be using up one of these axes, so maybe it's this one. And then the y and the z-axis are free for my p orbitals. And we're going to draw that picture in a second, too. So you'll get to see that in just a second. All right, I believe, yeah, there's the diagram that I drew. I think mine looks a little better, but I did just draw it, so you know. All right, so here's our sigma bond right here. We'll label these again. Sigma, sigma, sigma. And then our pi bond is the resulting overlap between this guy and this guy. Now, in some drawings, what they do is they don't try and do the balloon thing that I did, but like this. What they instead just do is they draw these dashed lines to say, oh, these are overlapping. We just spread out the diagram so that you could see it. Because in reality, these are all going to be a lot closer together to have that overlap possible. All right. So this is the part where I would have you draw balloon diagrams of these. How can you tell if it's sigma or pi? So remember that something is sigma if it goes along the internuclear axis. So if I can draw a line between the two nuclei and my electrons go through it, it's sigma. So there's all my nuclei here. Oops, I didn't mean to erase the pi. These electrons right here are not on the internuclear axis. They're actually above it. So this must be pi electrons. But all the other electrons I've circled, you can see that my blue line went through them. So the blue balloons do not go through the internuclear axis. And that's where this is right here. So these are overlapped along these dashed lines. It's just that with their diagram here, let me put my diagram up at the same time. And then maybe that will make more sense here. So you can see what they were trying to do. There we go, that works. And you could compare it with mine. And they are trying to express the same idea, but they're doing it differently. I personally like to show the overlap because it makes more sense than drawing where this weird dashed line come from. But different textbooks do different things. I have another example in a second that's going to show just SP, and they draw it like I do, and I'm going to draw it that way too. Now remember that in the orbital that I drew, remember that the p orbital in both sides counts as one bond, right? In other words, this whole thing here, and I'm going to draw it over my picture in red here. This whole thing is a bond. It's not two bonds, it's just one bond. You can't see what I was writing there. I wrote one p bond, which is not actually a thing. One pi bond. So now I can go like this. And we'll put that up there. And in the diagram on the PowerPoint here, so that's the wrong color. It changed colors between PowerPoint and there you go. This whole thing right here is one pi bond. But yeah, that's a really easy mistake to make. And the way that you can see that this has to be one bond is that if you look at this diagram right here, there's only one set of electrons in the dashed line. Down here, there's nothing. And the reason for that is all of this is one bond. All right, let's talk about sp hybridization. I'm not going to do these examples just because seeing the balloon diagrams probably... I'm not going to make you do this. I'm gonna show you a picture and ask you to identify it. I want to talk about bond rotation in a second. I want to do sp hybridization real quick. So if I want to make an sp hybridized orbital, that requires me to have 2 pi bonds coming out. So if this is my hybridization here. This would be required for my geometry in order to make something linear. Since there's only 2 electron domains, I need it to be sp hybridized to get a linear shape. On my diagram right here, the top bond and the bottom bond here must be my pi bonds. So we would hybridize these orbitals, and I get something that looks like this in my diagram. So let's draw the balloon structure for that real quick. I'm going to make this smaller, though. Let's see here. Yeah, I kind of just have to get rid of it, don't I? That's okay. So we got SP and P and P. So what I'm going to draw first, I'm going to draw the SP orbital. Here's my origin. So red is my SP. This is just 2 of them, but it looks like a P orbital. Now I'm going to draw P going up and down. And then I'm going to draw P going front to back. Because there's really only one orientation that's left. It's this way, right? Now I got to bust out the eraser and do this. And there you go. So that would be my carbon with sp hybridization. Where again, the red one is the sp orbital. Now if I had another carbon right next to it that was doing the same thing, here's where its sp orbital would be. Here's its other sp orbital. And then I would just do the same thing. I would have my p orbital going in the up-down direction. And then the p orbital going in the front-back direction. And then I got to tidy up. And now what I have to do is I have to do the same overlap thing that I did before. So I'm going to overlap the up and down orbitals first, which is these guys. Obviously, this is much easier to do when you have PowerPoint and you can just erase stuff. So that's just like before. But now I got to do the same thing with the blue ones, because the blue ones are also side to side. And so we're going to take this guy and this guy. We're going to do the same thing. And this one's in the back. And there you go. So now I'm going to shade them in so it's a little easier to see. So here's my blue guy. He is in the front. This red stuff should actually be gone. This blue orbital is in the back. There's my blue. And then the black one goes up and down. And the red one goes side to side. All right, hopefully that looks okay. It looks okay to me, but I know how to do this stuff, so. In the middle, if I were to draw this thick red line for my internuclear axis, here's where my sigma bond would go. Here's the pi bond number 1 that we said before. And then finally, front to back, here's pi bond number 2. Yes, you found the Eye of Sauron. It's in the middle of acetylene. It's sp hybridized. All right, so let's go back here and let's see how I did. This is what it was supposed to look like. Did I do okay? It's not bad. I think in this case, their diagram is a little better than mine. But you can see that in our diagram here, the sigma bond is the purple one that's in the middle. Right here. Here's our sigma bond. And then our pi bonds are the ones that go top and bottom here. And also front to back. So each plane is a pi bond. Just like we said before, the top bottom part constitutes one bond, and the front back also constitutes one bond. So it looks like you have 4 bonds there, but in reality, it's 2 bonds. The only difference between my diagram and their diagram is I didn't put the H's on. So yeah, so I would have an H that goes over here and over here, but I didn't do that. But yeah, this should be SP. So there you go. If you have SP hybridization, you're going to have 2 pi bonds. If you have sp2 hybridization, you're going to have 1 pi bond. And if you have anything else, you're not going to have pi bonds at all. So you're not going to have pi bonds for sp3 or sp3d or sp3d2. At least not in this class. All right. Now, looking at this diagram, I'm going to hit clear to get rid of all this ink. If I was to take this atom right here and torque it so that I rotated it around, could I do that without breaking the bond? So I'm going to take this atom and rotate everything around this way. Would the bonds stay bonded or would I break them? The way to answer this question is imagine that this was a balloon that you held in your hand and you're holding carbon 1 in your left hand and carbon 2 in your right hand. Can you twist carbon 2 without popping the balloon? Like, could you make this spin around? And the bonds would stay bonded. Well, let's actually go back to that slide here. Hold on. Let's go to this instead here. What am I drawing on this? Do you have a more specific question that I can address? Where is my marker? There it is. Okay. So if I have two atoms that had a pi bond. Yeah, if you have a question that you can bring up, because remember, tomorrow is also office hour. Because we can discuss this in more detail tomorrow as well. All right, so let's suppose that I have a pi bond here. Could I rotate this 180 degrees and keep stuff bonded together? And when I say rotate this 180 degrees, I mean specifically this side. This one's going to be fixed. And the answer is, well, if you do that, then this is what would happen. The left side is fixed, so it stays like this. But now, the other side is like this, and they no longer overlap. Because this was the original position along this axis, right? The end result that we get here is that if you rotate a molecule with pi bonds, the pi bond breaks. Now, bonds don't just break, right? If I make a bond, the molecule is going to stay bonded. Those electrons are going to need a lot of energy to get nudged out of that configuration. In other words, if you have something with a pi bond, you can't rotate it. And the reason being is that if I rotate this side, this overlap goes away, and I break the bond. I can't do that. That would require a lot of energy. So molecules that have pi bonds don't rotate. But molecules with single bonds do. So if I had a carbon that had just an sp orbital, or not an sp orbital, sorry, an sp3 orbital like this, we could draw the other orbitals like this. I could spin this guy around all I want because this will stay overlapped. Since the overlap is all that I care about, because the orbitals need to stay overlapped in order to keep the bond going, sigma bonds rotate freely, and pi bonds don't rotate at all. So what that means is if I go back to this structure right here, and I drew these three Lewis structures, I have a Cl on both sides here, but in this case, they're offset from each other. But because I can rotate this guy around, like so, and I get the same thing, these two are the same molecule. In chapter 1, we talked about isomers. Maybe it's chapter 2, I forget. But these are not isomers. These are actually the same thing. However, on the next example that I have here, these molecules can't rotate. So if I try to rotate this around, I would break the double bond. So this is not allowed. Which means that these molecules are stuck with the CLs in different positions. So these are isomers, and these are actually isomers that have names that you have probably heard before. Now, what's funny is I heard all of these terms in chemistry, and most people hear these in the news, but this one's called cis, and this one's called trans, because what cis means is same. In other words, they're on the same side of the double bond. And trans means different, they're on different sides of the double bond. And you've heard the prefixes cis and trans in current social discourse. Currently, our movement during the month of June, being Pride Month, is to fight for transgender rights, trans being somebody who is transitioning between genders. And so that's what these terms mean. They also apply in chemistry. They're just prefixes. Now, because the cis molecule is stuck with these on the same side and the trans molecule is stuck with these on different sides, they are unique molecules. And so what that means is that if I put this in a bottle and I sold it to you, and I put this in a different bottle and sold it to you, you bought two different things. And so these don't convert between each other because they can't rotate around the double bond. Now, because double bonds don't rotate, the same thing is true for triple bonds. They can't rotate either. Because you would be breaking two pi bonds in that case. All right, that's bond rotation. The last thing that we have to talk about really is that... Oh, here, I'll actually put the names of these on the board here. I didn't want erase. I want erase all. So here are the names of these molecules, just in case you were curious. These are their chemical names. We actually do have to include the cis and trans prefix in order to differentiate them. Because if you just said 1,2-dichloroethene, somebody would say, well, what side of the bond are they on? You have to tell me if it's cis or trans. The last thing we want to do is talk about hybridization with things that aren't sp or sp2. So if I want to do something with sp3d, or in other words, I need 5 electron domains to make a molecule, this would be something that is trigonal bipyramidal. And my structure would look like this. Oh, sorry, I could also do this with sp3d2. And then here's some examples. So something like this, ASF5, would have this geometry, where here's my central atom, and then each of these is an sp3d orbital, bonded to an orbital on fluorine. Here are my sp3d2 orbitals for sulfur, each of them pointing in a direction of the shape. Since I'm bonding with fluorine, it's just got unbonded fluorines on here. Technically speaking, this is wrong. I don't know why this textbook did that when I was using this. Because these atoms are bonded, these should actually be sp3. In reality, I think the answer to that question is a lot more difficult. But for this purpose, we're really only going to count central atoms anyway. So you only need to know the hybridization of a central atom. So to summarize what we covered today. This chart is going to be important for you to know. I don't really need this anymore, so we'll just do that with it right now. You'll need to correlate a geometry with a hybridization. And then when I show you balloon pictures like this, you're going to have to tell me what orbital is involved from like a drop-down list. I might ask you, can this molecule rotate, or are these two molecules the same? I'm not going to ask you to draw any pictures, because obviously that would be impossible for me to evaluate. But that's it. It's mostly just going to be related to that chart that you see on the screen and identifying the pictures that I showed you today. And bond rotation. Because I think that that's pretty much it. Yeah, here's the same chart that I just gave on the Photoshop screen. And so that's how we match hybridization to geometry. So I think I have a practice problem. Oops, yeah, here's the last slide of the quarter. So draw the Lewis structure for each of these molecules. And in the central atom, what I want you to do is tell me its hybridization. So if you draw the Lewis structure for HCN and you say, oh, it has this geometry, therefore its hybridization must be this. When it says hybridized structure, that means a balloon model. You do not need to draw the balloon models. You just need to recognize them. So go ahead and do this. Draw these Lewis structures. And when you're done, type in the chat what the hybridization of the underlined central atom is. Okay? We'll go over the answers in just a second. And then we'll be done. Hooray. All right, just a few more seconds to finish up. I just quickly drew the Lewis structures on my PowerPoint here. Is this doing what it's not? Ah. See, you could do it. Just gotta believe. That didn't work. Hold on. That'll work. There we go. All right, so HCN. You should have drawn a Lewis structure that looks like this. There are 2 electron domains, which means that I need to have sp orbitals. And you can actually see that right here. So this would be my sigma, and this would be my sigma, so I need 2 of them for sp. The other 2 that I didn't draw in blue would be pi bonds. Now this second one, I didn't actually realize that I had an sp3d3 in here. But you'll do the counting here, and if you drew the right Lewis structure, you get 7 electron domains, which is sp3d3. I'm going to try really hard to avoid putting sp3d3 on the test. That's not intentional. Pretty much anything with xenon ends up being weird in some way. Back to normal stuff. IF5 has 6 electron domains, which means that I need 6 places to put electrons in. That would be sp3d2. And then I3-, when you draw its Lewis structure, there's 5 domains around the central atom, so that would be sp3d. Remember, the geometry and the hybridization match up 1 for 1. So if you know the electron pair geometry, you always know the hybridization. You just got to go back to this chart, which is on... Oops, that's not what I meant to do. That's not what I meant to do. That's what I meant to do. This chart here. And with that, the next thing you must do is celebrate. Because we are done with Chem 161. Break time back in never. Oops, that's the wrong thing. What am I doing? I'm destroying my scene now. I turned this off for some reason. So that's it. There is no more content to cover. The molecular orbital theory part on the slides is not something that we're going to cover in this class. Mostly because, 1, we don't have any time, and 2, you won't see it again, most likely, until organic, and if we need it there, I think Steve talks about it in his class, so that's fine. But yeah, so all of the content in Chem 161 has been covered, which means that on the final exam, you'll have an assessment that goes over everything in the class from Chapter 1 all the way through Chapter 6, including this stuff, so like there will be extra questions in there. I would definitely recommend doing as many practice problems in the textbook as you can. Make sure that you are doing the quizzes early. I am going to try and release the quiz tonight. I just want more people to take the quiz. So after my other lecture, I will unlock Chapter 4 quizzes so that you can study for them. Make sure that you get all the information that you need out of those. Because there will be some unexpected surprises on the final exam. Extra questions that you haven't seen, because I don't use all of the questions from the quizzes. I do use some of them, though. And then Chapter 5 stuff, which I will add in there, because I'm going to work on that later today. Since this is the last lecture, this is, I guess, where we say goodbye. It's been fun. It's been real. And I hope that when you look back on this quarter at the very end of this pandemic, whenever all of this settles, I hope that you look back on this class and remember something from it. thanks for watching, and best of luck to you wherever you end up from here. Chem 162, hopefully. See you around.